Okay, good afternoon, ladies and gentlemen. My name is Alberto Sabora, and I'm going to speak about a finite fracture mechanics approach to the asymptotic behavior of few-notch structures. I would like, before starting, to thank the other authors of this work, Professor Carpinteri and Dr. Cornetti from Politecnico di Torino. Well, in order to deal with brittle or quasi-brittle materials, a new failure criterion has recently been proposed. The criterion is named finite fracture mechanics, FFM, and it's based on the hypothesis of a finite crack advance delta. So in other words, it is supposed that fracture does not propagate continuously but by finite crack extension, which is denoted by delta, and whose value could be determined by the contemporaneous fulfillment of both a stress requirement and an energy balance. So this is how the criterion reads. The first condition requires that the average stress upon a crack advance delta must be higher than the material tensile strength sigma u, while the second condition requires that the energy available for a crack advance, for a crack increment delta, must be higher than the fracture energy Gc. So the failure load is attained when the inequality is strictly verified, so when they are replaced by two equations. So the system becomes a system of two equations in two unknown. The crack advance delta and the failure load sigma f, which is implicitly embedded in the function sigma y and g. From a physical point of view, we can say that fracture is energy driven, but a sufficiently high stress must act in order to trigger crack propagation. Notice that a similar criterion, but based on a pointwise stress condition, was also put forward by Leguillon in 2002, and that these two coupled criteria led to overcome some drawbacks related to the other criteria previously introduced, which were based only on stress or energy requirements. Finite fracture mechanics has been applied to several geometries and materials, such as, for instance, concrete beams to predict size effects, V-notch structures, matrix inclusion debonding, composites, and it has also been implemented numerically. And in the present work, the criterion is applied to brittle U-notch structures subjected to mode 1 loading, and this will be the first part presented by myself, while the second one will deal with the lamination along an elastic interface and will be presented by Dr. Cornetti. So we can start by having a look, indeed a very brief look on what it has been done for V-notch structures. That's the geometry. Omega is the notch opening angle, sigma is the remote stress field, and so we are considering mode 1 loading condition. Here I have written the finite fracture mechanics and the energy balance according to Ewing's relationship through the function K1 of G, which is the stress intensity factor related to a short crack of length stemming from the notch tip, and to the fracture toughness K1C. And by assuming that failure takes place whenever the generalized stress intensity factor, K1 star, also known as notch stress intensity factor, reaches its critical condition, which is legitimate within brittle structural behavior, we succeeded in obtaining the analytical expressions for the generalized fracture toughness, K1C star, and the crack advance delta. So we can see that both these functions depend on the material properties to K1C and sigma u, and to the notch opening angle to this function lambda, which is the solution of the classical eigenvalue problem derived by Williams in 1952 and mu. So now the crack advance depends also on the notch opening angle and becomes a structural parameter. Now the question is, what does it happen in the case of U-notch structures? We can start by considering an elliptical hole in an infinite plate under remote tension. We denote the length of the two axes by 2a and 2b. We denote with k the ratio between the axis length, and with R the radius of curvature. In order to apply the finite fracture mechanics, we need the two functions: the stress field ahead of the notch tip and the stress intensity factor related to a short crack of length T stemming from the notch tip. Okay, for what concerns the stress field ahead of the notch tip, the problem was solved by Inglis in 1913. Here we have written just the stress field, the full stress field in Cartesian coordinates. So, as it can be seen, it's a function of both hyperbolic sine and cosine functions. And clearly for x or s equal to 0, so when we are at the notch root, the stress field attains its maximum value, and the ratio between this maximum value and the remote stress field is named stress concentration factor. For various, this is the full stress field. For very slender notches, we can also use the approximation introduced by Greger and Paris in 1967, which could be defined to this parameter K1U, which is known as apparent stress intensity factor. And these two stress field functions will be sufficient for our study, even if other expressions are also available in the literature. Okay, this is for the stress field. Now, the second function is the stress intensity factor of a crack at the notch root. The length of the crack is C. And the stress intensity factor could be expressed in this way, through this factor F, which is a geometric factor. And different expressions have been proposed in the literature for F. Here we have chosen the following one due to Lucas 1987, which provides error within 5% as long as this condition is satisfied. So, for very slender notches, these relationships keeps true for any ratio C over R. So by substituting this expression in the previous one, we get this finally equation, and while for k tending to infinite, we get the stress intensity factor related to an edge crack in a semi-infinite plate under remote tension. For k tending to 0, which is the crack case, we get the apparent stress intensity factor up to a multiplicative constant nearly equal to 1.056, so an error of about 5% as expected. So now we have the two functions, and we could insert them in the finite fracture mechanics criterion, which in critical condition, that is when the apparent stress intensity factor reaches its critical conditions, reads in this way. So R bar here is the dimensionless notch root radius. Sigma tilde and G tilde are two functions that could be obtained analytically, also indeed they have been obtained analytically, by integrating the two functions sigma y and k1 of c. And delta c bar is the dimensionless finite crack extension, while K1 Cu bar is the dimensionless apparent fracture toughness. So this is the criterion, and this is a system of two equations in two unknowns: the finite crack advance of delta C and the apparent fracture toughness K1 Cu. And these are the results that we have obtained for what concerns the apparent fracture toughness, the dimensionless apparent fracture toughness, plotted as a function of the square root of the dimensionless notch root radius. As it can be seen, the apparent fracture toughness increases as R increases as expected, and this for every k. While, well, notice that these curves are all limited by the validity of the relationship derived by Lucas, while for very low values of k, for instance 0.001, the notch becomes more sharp, so when R tends to 0, the curve approaches the unit value, that is the apparent fracture toughness approaches the fracture toughness of the material. And this is for what concerns the appearing fracture toughness. On the other hand, the second unknown is the finite crack advance, and here we have plotted the solution as a function of the notch root radius R. So how it can be seen, the crack advance depends on the notch root radius R and slightly on the ratio between the axis length K. So differently from the simple stress or energy criteria, the crack advance is a structural parameter and not only a material property. And well, finite fracture mechanics prediction will be now compared both with experimental data related to 3 or 4 point bending tests on ceramic U-notched samples, and with results obtained by different criteria based on a critical distance. Indeed, since in a recent work by Gomez et al. Dated 2006, it was shown that all the criteria based on a critical distance provide very close predictions. We just decided to focus our attention on the simple average stress criterion proposed by Neuber in 1958. This is the stress condition, and this is delta, the finite crack advance, which is a material property. Just important to underline the fact that since in the test specimen the notch root radius is smaller enough with respect to the other geometric dimensions, we can use the Premier-Parks expression to approximate the stress field. And these are the two expressions according to the two criteria, the average stress and the FFM, for what concerns the dimensionless appearing fracture toughness. So actually, this one is much easier to be applied since this one requires the solution of a nonlinear equation. And these are the results. Well, for data sets have been taken into account 3 different materials. Well, before starting, I must say that in these 3 cases, just to be honest, since the material strength was not provided in the reference paper, we have obtained them from a best fit procedure. And well, the continuous line here refers to the finite fracture mechanics predictions, while the dotted line refers to the average stress criterion. So how it can be seen, both the predictions are in well agreement with experimental data and are very close with each other. The only significant difference is nearly R equal to 0, where there is an error of about 5% since due again to the approximation introduced by using Lucas relationship. And just to conclude this first part, what it has been done is the application of finite fracture mechanics criterion to brittle U-notch structures subjected to mode 1 loading. So the main approximation is due to the stress intensity factor related to a crack stemming from the notch tip, as we have mentioned, as we have seen. And it's important again to underline the fact that predictions are in well agreement both with experimental data and both with predictions provided by the other fracture criteria based on a critical distance. So for brittle U-notch structures, the simple average or even point stress criterion can thus be applied to get sufficiently accurate results. And this is the end of the first part. These are some references that I've cited during my presentation or are somehow connected with it. Now it's Dr. Cornetti. Thank you.
So you've got 15 minutes because we are approaching the dangerous moment of coffee break. Okay. So if you take 15 minutes, there will be more discussion.
Okay. So first of all, I want to thank the organizers for having given me the opportunity to speak about some recent advances in my research activity. Just I want to say that we speak about a second application of finite fracture mechanics to the problem of the bonding along an elastic interface. And beyond the previous authors, this work, current work, is done in cooperation with Professor Matic from the University of Seville. So, in order to introduce the problem, let's consider on the left side 2 pieces of the same material perfectly bonded, that is the homogeneous medium case, and on the right side we have the same pieces of the same material connected by an elastic interface, that is a bed of springs of stiffness K. So in the left case we have no displacement discontinuity across X and we have a singular stress field, whereas in the right case we have displacement discontinuity because the interface is deformable, but we have no stress singularity. For what concerns the strain energy release rate, in the homogeneous medium case is given by Irwin's relationship, whereas for the elastic interface case, the strain energy release rate is given by the square of the maximum stress divided by twice the spring stiffness. For what concerns this last formula, I should say that I derived in a recent paper this formula for a mode 2 delamination in this geometry by evaluating the crack closure work. Later I realized that the formula is already known in the literature, at least since the work by Lenchy, which derived the formula in mode 1, but I think maybe it dates back even earlier. But to my best knowledge, this formula is not yet very well known yet in the literature, where G, also in the case of the elastic interface, is often evaluated as the derivative of the strain energy of the bull structure with respect to the crack length at constant load. And of course, this evaluation is more complicated than this formula. Anyway, these expressions are reasonable in the sense that G is nothing else than the strain energy stored in the first spring at the crack tip, or in this case, in this spring. Getting back to the previous schemes, if we can compute the G, we can apply linear acid fracture mechanics. That in the case of elastic interfaces can be written in terms of stresses. As well known, I want to make you observe that as well known, linear elastic fracture mechanics cannot be used to predict crack initiation in the homogeneous medium case, whereas at least in principle it can be used to predict crack initiation in the case of elastic interfaces, since the stress remains finite. Anyway, for short cracks or zero cracks, it is expected that finite fracture mechanics should provide better results. And so here are the expression of finite fracture mechanics for the homogeneous medium case and for the elastic interface case. You see that in these second inequalities I substitute the formula for the strain energy release rates previously shown. When applying finite fracture mechanics to elastic interfaces, the failure load depends on the dimensionless parameter alpha, whose definition is given here, which rules the ductility brittleness of the interface. The meaning of alpha is evident if we consider a cohesive interface with a linear softening. Alpha is nothing else than the ratio between delta F over delta P, and therefore alpha equal to 1 means an elastic perfectly brittle interface. Alpha equal to infinite means an elastic perfectly plastic interface. So here are the two expressions for finite fracture mechanics in a mode 1 delamination or a mode 2 delamination. In order to check the capabilities of the method, we simply considered a couple of very simple geometries. The first geometry I'm going to consider is the pull-push test, which is a kind of double lap joint. So here is the geometry. In this case, the delamination occurs under the prevailing mode 2 condition, and therefore a simple model can be achieved by discretizing by modeling the adhesive layer as a bed of horizontal springs. If the interface were rigid, the critical load is given here and is constant with respect to the bond length. On the other hand, if the interface is deformable, we get a second order differential equation in the relative displacement which with proper boundary conditions leads to this solution for the stress field, where the parameter LCH appears, which is a characteristic length function of the material and geometrical properties of the materials and structure. We can get the maximum stress, and so therefore we can apply we can obtain the critical load according to linear elastic fracture mechanics with the formula previously derived, and we can apply as well as the stress criteria. We can apply also finite fracture mechanics. In this case, we have a system of two equations in two unknowns that can be managed to get a unique equation that has to be solved numerically. and we can get here the dimensionless failure load, which is a function only which depends only on two dimensionless parameters. One parameter is alpha, ruling the brittleness of the interface, and the second parameter is lambda, which is the ratio between the bond length and the LCH. So here is the plot of the dimensionless failure load versus the relative bond length, and you see that the finite fracture mechanics prediction are comprised between the stress criterion and linear elastic fracture mechanics in case of compliant interface, say an energy criterion. You see also that finite fracture mechanics is able to capture the transition between the stress governed failure for short bond length and the energy-based failure for long bond length. Here is the same plots for different values of the parameter alpha, and you see that increasing alpha, it increases the gap between the stress and the energy criteria. Here is another plot. We compared the solution with the one obtained by the closed zone model with a linear softening branch, and you see that the two predictions are in excellent agreement. Also, I must say that the finite fracture mechanics prediction are much more easily to be obtained with respect to the closed zone model. Here are the comparison with other models based on critical distances. Just I want to say that again, finite fracture mechanics is the one providing the most, the closest prediction with respect to the cohesive zone model. The second example I considered, I will skip any analytical details, is the double cantilever beam test. Again, the interface between the two cantilever beams can be modeled by a bed of vertical springs, as in the model by Kamin in 1973. We can evaluate G as done before, and therefore we can apply linear finite fracture mechanics. And here is a preliminary result. You see that in this case the dimensionless critical load is a function not only of alpha, the parameter ruling the brittleness of the interface, it is a function also of lambda, the relative bond length, and of gamma, which is the relative crack length. And you see in this plot how the failure load decreases as the relative crack length increases. So here are some conclusions. Just I want to say that the model can be used to obtain analytical estimation of the elimination load for cellular geometries, which is our aim. But I want to say that further analysis are needed to investigate if the criterion has a physical background, or if we must look at it just as a good way to obtain the critical load in agreement with the cohesive zone model. And the second point is that further analysis are needed to generalize the criterion to mixed mode elimination, since in this presentation I consider only mode 2 and mode 1 separately. And here are some papers I cited during my talk. Thank you very much.
So we have time for discussion.
Well done.
Any questions?
Very well controlled.
I told them to hold the coffee for us.
Yes.
Yes, a short question. Is there any possibility to use finite fracture mechanics in three-dimensional components?
Okay, this is a good question. Up to now we consider...
Well, there is the coffee practice, the answer.
Okay. We haven't yet think about this problem. Up to now we consider only two-dimensional situation, or almost three-dimensional. Okay.
You could certainly imagine it anyway, but you would have to decide, do you want to say a semi-elliptical crack which grows always with the same shape, or do you want to say it could have different shapes? And no, but at least in principle you can do it.
Okay, any more questions? No. I don't see those. Thank you. Yeah, there is one. So you want to...
No, I was just wondering, because I never did it, but I always assumed that with the cohesive zone model you would get a similar kind of result from the finite fracture mechanics. And because both models are similar in the sense that there is a distance which comes out of it, but the distance is not known a priori, you know, it just happens. So are the distances the same actually in both models?
Yes, I agree. Well, the Quintessential model is widely spread in the community, so I think this is a good result. And I would like to say that in this case, for elastic interfaces, if delta is kept constant, we have problem with very short bond lengths. And in this case, the fine fracture mechanics is able to overcome this kind of problems.
Okay. Well, I would like to thank everybody, and particularly those who are really making effort not to fall asleep. So very, very nice, and thank you once again. And,